Today we are going to learn about the excess pressure on curved surfaces. Let's let's draw a surface like this and imagine this surface has two origins like this. And due to the excess pressure, suppose this surface expanded a little bit like this. These dotted lines represent the expanded surface. Suppose the length of this side be x and this side be y and this distance be r1 and this radius to be r2, and suppose this expanded side have a distance x plus delta x, and also suppose this expanded side of y have a distance y plus delta y. Let's denote this unexpanded area by a, b, c, d and this expanded area by a dash, b dash, c dash, d dash. And let's take this normal distance between expanded and unexpanded surface be delta z. Let's denote this origin be O1 and this origin be O2. Let me draw this triangular shape as a separate figure. This is A dash, this is B dash, this is O1 and this is AB. The triangles A dash, B dash, O1 and AB, O1 are similar triangles. So we can write A dash, B dash by A dash, O1 is equal to AB by AO1. And also let's draw this triangular shape separately. This is B dash, this is C dash, this is O2, this is B, this is C. Here the triangles B dash, C dash, O2 and triangle BCO2 are similar triangles. So we can write B dash C dash by B dash O2 is equal to BC by BO2. We know that the excess pressure is just a pressure difference between the pressures that acts above and below a surface. So let's take the excess pressure on the concave side to be P. This implies the outward force on the element A, B, C, D is equal to Pxy, where this xy is just the area. This is that area. So let's find the work done by this outward force on the area element ABCD. So this work done is W is equal to force into normal displacement. We know that the force is P into xy, and also we know that from this figure normal displacement is delta z. Delta z. Actually, work done by this excess pressure P should be equal to the increase in surface energy. So we can write work done by excess pressure P is equal to increase in surface energy. And this is the most important formula that we need for our further derivations. So let's first find the increase in surface energy. Increase in surface energy is equal to surface tension T, capital T, into increase in area. Let us take this as equation 3. We can write this equation 3 as T into increase in area. Increase in area is actually the difference between the area of A dash, B dash, C dash and A, B, C, D. That is the area of A dash, B dash, C dash minus area of A, B, C, D. These two areas are like rectangles, so we can find its area by multiplying its sides. So we can write this as x plus delta x times y plus delta y minus xy. Open the brackets and take in the difference gives t into x delta y plus y delta x. And let's take this as equation 4. Let me rub this. Let us substitute equation 1 and equation 4 in equation 2. Equation 1 and equation 4 in equation 2, that gives p times x times y times delta z, which is equal to t times x delta y plus y delta x. From this we can write t times x delta y over xy delta z plus y delta x over xy delta z, which is equal to p. So p is equal to t times 1 by y delta y over delta z plus 1 by x delta x over delta z. We have the need to modify this equation for excess pressure by avoiding the deltas in y and z and x. So we can do it by considering the similar triangles A, B, O1 and A dash B dash O1. First, we have this equation. So A dash B dash over A dash O1 is equal to AB over AO1. So this is actually equivalent to x plus delta x over R1 plus delta z is equal to x by R1. Let me encode more details to this picture. So this side is x plus delta x, this is x, this is R1, and this is actually delta z, and in this triangle this is y, this is y plus delta y, this is R2, and this distance is delta z. From this equation we can write x plus delta x over x is equal to R1 plus delta z over R1, which gives 1 plus delta x over x is equal to 1 plus delta z over R1. 1 cancels from both sides and gives 1 by x delta x by delta z is equal to 1 by R1. Let's take this as equation 6. Let me rub this. Let us take the other pair of similar triangles. From the similar triangles BCO2 and B dash C dash O2, we can write B dash C dash over B dash O2 is equal to BC by BO2. And this is equivalent to y plus delta y over R1 plus delta z is equal to y by R2. Analogous to the case of similar triangles A dash B dash O1 and AB O1, in this case also we get 1 over y delta y over delta z is equal to 1 over R2. Let us denote this as equation 7. Let us substitute equation 7 and equation 6 in equation 5. This gives excess pressure P is equal to T times 1 over R2 plus 1 over R1. Let us take a little more general case. Suppose if the surface with the radius R2 is convex, what happens? If it is convex, it have a negative radius compared to the concave side. So the excess pressure P can be written as T times 1 over R1 minus 1 over R2. So we can write the more general expression for the excess pressure P as, so the more general expression as P is equal to T times 1 over R1 plus or minus 1 over R2. Let us study some special cases of excess pressure using our general expression for excess pressure. So, the case 1, liquid drop. We already know about the liquid drop. It only have a single surface. This single surface have uniform curvature throughout its area. So we can write this single surface have R1 is equal to R2, which is equal to R. So this gives the formula for excess pressure P as T times 1 over R plus 1 over R, which is equal to 2T by R. Let us take the bubble as our case 2. For a bubble, it have two surfaces. These two surfaces have uniform curvature throughout its area. So we can write simply the excess pressure P as 2 times 2T over R, and which is equal to 4T over R. Let us take a bubble inside the liquid as our third case. Bubble in a liquid. Bubble in a liquid have only one spherical surface because its outside is filled or covered with the liquid. So we can write inside the liquid bubble has only one spherical surface. So this implies the excess pressure P is equal to 2T over R.